I'm Anjali Mishra and I'm a student from IISER Kolkata. I'm going to be your host for today's session and I'm very thankful to Hemant sir and the entire NASNI team for this opportunity. I'm one of the office bearers of the Astronomy Club Singularity of my institute IISER Kolkata, and today's session is a platform for collaboration with Astronomy Club of our institute and NASNI, for which we are extremely grateful and we look forward to this partnership. Before dive deep into this talk by our reputed guest, let me introduce a very special initiative that's going to enrich your astronomical journey in NASNI, the National Astronomy Network of IAPT. NASNI is a national platform initiated by the Indian Association of Physics Teachers, IAPT. It's designed to connect new sky gazers like many of you with astronomical experts, planetarium professionals, astrophysicists, and even popular public figures in sky watching. Because sky gazing becomes more meaningful when we share it with mentors who can guide us, with tools and events that inspire, and with a community that shares our excitement. NASNI is that bridge between the beginner and the expert, between curiosity and knowledge. So, dear friends, NASNI is here to guide and grow with you. Welcome to the network. Welcome to NASNI. I take the privilege to acknowledge some of the very special people present in today's session, including our chief guest, Dr. Nitu Borgohain, Hemant Kumar sir, Dr. Ranjita Das, and all the other dignitaries from IAPT and NASNI. Your presence enlightened this session like nothing else. We are truly grateful for having you here. As Carl Sagan said, something somewhere is waiting to. So before taking any much time, let me take the privilege to introduce our today's speaker, Dr. Nitu Borgohain. He is a distinguished academician and a researcher currently associated with the Assam Royal Global University, Guwahati. He has an extensive background in physics with a strong focus on astronomy, astrophysics, and quantum optics. Throughout his career, Dr. Neetu has demonstrated a deep commitment to scientific inquiry and education, contributing significantly to the academic and research landscape. He has more than 40 publications in national and international journals of repute. He has been actively involved in various research projects funded by DST and other funding agencies that aim to acquire advanced knowledge in his field. Dr. Borgohain has also been instrumental in organizing seminars, workshops, and conferences that facilitates knowledge and knowledge exchange among students and researchers. He is also the nodal coordinator of Northeast for ISRO's START program. Through his work at RGU, he continues to inspire students and contribute to the growth of the institution, strengthening its reputation as the center for higher learning and scientific exploration. Dr. Neetu, we are extremely grateful to have you here as our guest. And without taking much time of yours, I would like to I would like you to take over the session. Thank you.
Thank you so much, Miss Anjali. Uh, I I'd like to thank the organizers of NASNI as well as the IAPT for inviting me for this talk. I'm sharing my talk now. Hope it is visible.
Yes, sir. It is visible.
Okay.
Yes, sir.
Okay. The title of my talk is From Stardust to Supernova, the Evolution of the Stars. Here I am going to discuss how the stars are getting birth and how they are demising, as well as how we can have a track on the evolution of the stars. Starting with, yeah, yeah. This is a beautiful night sky, and the night sky is full of celestial events. Uh, in each day, some events are occurring. Say, for example, if the sky is clear, we can see the twinkling stars. The twinkling stars basically observe in the around 30 degree from the horizon, because the lights which are coming from very distant star, and they are whenever they are entering into the atmosphere, they has to they has to come through the lots of particles which are there in our atmosphere, and because of that interaction with the atmospheric particles, the light the seems like to be twinkling like these. So we can see the twinkling stars or sparkling stars around the region which is around 30 degree from the horizon. Then we can see the constellations. These are the group of stars, and we imagine different structures combining these groups, and those are called constellations. And here you can see the Orion constellations, which is uh, which can be seen in the form of a warrior having bow and arrow. So we can imagine these things like this stars, group of stars like this. Then shooting stars, sometimes the meteor or meteorite falls.
Excuse me,
Yeah,
Dr. Nitu. We are
yeah.
we are looking only first slide.
Let me stop it again and
Yeah.
reconnect.
Yes, yes. Only first slide is visible. Yes. Now it is visible.
Now these animations are also visible,
Yeah.
sir?
Yeah. Yes. Yes.
Okay. So I was talking about the sparkling stars or the twinkling stars and the constellations. Here, this is the Orion constellation, shooting stars that already that I have spoken. Then eclipses, solar eclipse and the lunar eclipse. The solar eclipse is very, if we see the total solar eclipse, that is very beautiful to observe, and lots of things that of the sun, which usually not seen, that can be visible, like the diamond ring. That is very interesting to see, observe. Lunar eclipse, we can uh, yeah, we can see the lunar eclipse, and in September, coming September, we will be observing one lunar eclipse, which will be there in India. We can observe it from India. Planet conjunctions. Planets, sometimes they are coming closer, and when they come closer, then we can call it a conjunction. And recently we observed a planet parade that was very spectacular to observe. So if we observe the night sky by our naked eye, then if you start counting, then around 5,000 stars you can count. And these stars can be categorized in different groups. And these there you can categorize in 88 constellations. Among these 12 constellations, which are in the path of our sun, and we call them as zodiac constellations. So these all are stars. You can see this sky. Whatever you are seeing, wherever you are seeing any spot, any dot, that that is a star. So, okay, so the whole sky is full of stars. So now I'm going to discuss how these stars are getting born. What are the ingredients of a star? So it start from the stellar nursery. Stellar nursery is nothing but a dense molecular cloud, and these molecular clouds are mostly made up of hydrogen, and along with other dust particles. Along with hydrogen, some amount of helium is also present. So it is, we can see here this Orion Nebula, which is there in the Orion constellation. Here it is the Eagle Nebula, then Carina Nebula. These are the very prominent stellar nurseries where the stars are getting birth. So these places are cold and very massive. Cold, very massive, and often they're extended to 100 or 2000 light years across. And the reasons where gravitational collapse triggers the star formation. Here, in these areas uh, where the stars, dust are present, so gravitational collapse often occurs, and that produces the stars. So the primary ingredient, it requires hydrogen as well as helium and some trace element like we call these metals like carbon and other heavier elements like carbon, oxygen, etc. Those are in astronomy they are termed as metals, and the 2% of it is there in the stars, and the requirement is the gravitational pull should be there, and an extremely high temperature is required at the center such that the hydrogen to helium fusion can be achieved, which requires very high temperature and also high pressure, because if gravity will be collapsing any area or dust or molecular cloud, then definitely a high pressure will be created, and which will be once a star will be forming, then magnetic field will be there. So these are the ingredients of stars, and now we are going to discuss. This is the bird view of the life cycle of a star. It always starts from a stellar nebula or a molecular cloud, and then it goes to two direction. One is the upper part is for intermediate mass stars or low mass stars, those stars which is equivalent to our sun or the small stars like our sun, and the lower part is for heavy mass stars or the massive stars. In all the cases, this will be once the star will be forming, it will be entering to a phase called main sequence. Then it will be converting to a giant or red supergiant. Then there will be planetary nebula or supernova explosion. Then depending on the mass, it will be converting to white dwarf or neutron star or black hole. That will be discussed. Now, at the first point, we'll be discussing what is this phase, how this from the stellar nebula it becomes a star. So, yeah, this is the part of how a star get birth. So it's all start from the stellar nursery. A star begins to form in the nebula, a cloud of interstellar hydrogen gas and dust. This happens when any area of a stellar nursery get disturbed by any other entity, and because of that it start collapsing. The gas and dust compress due to gravitational force and forming a slowly rotating globule. So here, the gravity will be taking all the materials, trying to all the materials to pull it in, and eventually a gas pressure will be created, which will be trying to pull it out. So because of that counter forces that the global will be start rotating. Then the gravitational force will be overcome the gas pressure, and because of that, it will be more collapse. And when it will be collapse, it will be it will be start spinning very heavily, and because of that, a disk, it will be forming a disk, or we call it a protoplanetary disk, and the core will be formed here, which will be all the mass will be getting accumulated at the core. So here it is the spin, pressure, and the temperature. Here, all this will be increased, and the global will be differentiated into protoplanetary disk, which may be becoming the planets. This disk, from this disk, the planets will be formed later, and the central core, which will be forming the star. This is a typical formation of a typical star, like our sun and its solar system. So in the second part, what happens in the protostars and the protoplanets will be formed. Here, one thing is to be mentioned that a protostar will be just a born star where gravity will be taking all the materials in, and gas pressure will be taking trying to all the materials out. So there will be a balance between this gravity and pressure. So at some moment, this gravitational force as well as the force due to the pressure will be balancing each other, and that phase is called hydrostatic equilibrium. Not only for the stars but also for the planets, it will be occurring. Once that occurs, then a stable star will be forming. So this stable star it emits UV light and other radiations, and it can emit also the focus Z when it was forming. And then a young star will be formed, and this once this will be that hydrostatic equilibrium for for the star as well as the planets will be established, then this solar system will be stabilized. So the same process is followed by our sun. The sun is now stable, and the hydrostatic equilibrium is achieved, and once it will be happening, then its core temperature increases to some amount of 10 to the power 7 Kelvin, which is required to hydrogen fusion process. Hydrogen will be converting to helium, and a very huge temperature is required, and that temperature is achieved the moment it will be reaching the temperature. Then the star will be start generating its energy. Now we are going to discuss how the energy will be generated. So the energy, this is the energy production in the stars. Generally, we all know that we are taking the example of the sun here. Here, four hydrogens are getting converted to helium. So hydrogen to helium fusion process. Apparently, it can be shown by this picture. These are four hydrogens, and these four hydrogens get collapsed to produce a helium, and a huge amount of energy released. And we can see that the mass of this helium is lesser than the mass of this cumulative mass of these four hydrogens. So there is a mass defect. That mass defect can be considered as the equivalence to energy. So by Einstein's energy mass equivalence, we can see that a huge amount of energy, which is equivalent to 26.64 mega electron volt, that amount of energy has been released in one fusion process, only one reaction, only four hydrogen to helium fusion. this 26.64 mega electron volt has been released. Here you can see that energy per diffusion for hydrogen to helium, it's count as 4.3 into 10 to the minus 12 joule. And per second, in a second, there are 9 into 10 to the power 37 fusion reactions are going on the surface of the, sorry, in the core of the sun, and which produces around 3.87 into 10 to the power 26 joule amount of energy. And if we compare it, this amount, this energy, with the explosion of 15,000 ton of TNT, then it's equivalent to 6.27 into 10 to the power 13 joule, which was equivalent to Hiroshima bomb, the nuclear bomb that has been deployed in the Hiroshima during World War II. So you can see that how much energy, how much bigger this number is. It is around 10 to the power 13 numbers of 13 times bigger. So which is produced per second. So just in a second, this huge amount of energy is released by the sun. So you can now imagine how much of energy it is released. So there are two different process of production of stars, production of energy in the stars. For intermediate or low mass stars, it is it follows a different process, and the massive stars follows a different process. Intermediate mass stars, whose mass is equivalent to one solar mass or lesser, or equivalent to one solar mass. One solar mass is the mass of our own sun, which is 2 into 10 to the power 30 kg. So if the mass is of that range, then the process that energy production process that follows is called PP cycle, proton-proton cycle. In this proton-proton cycle, what we can observe that one proton will be collapse with club with another proton, and a neutrino beta particle will be ejected, and it will be forming a deuterium, H2, hydrogen 2. And at this moment, another proton will be, or proton means hydrogen, will be interacting with it, which will be producing a gamma ray, and also it will be converting to helium 3. In the same way, another reaction will be occurring, and from that reaction also another helium 3 element will be produced, and now these two helium 3 element will be clubbing together to produce a helium 4 and also a proton. So this way, four hydrogens will be clubbed together. Here you see one hydrogen, second hydrogen. Then from this, for production of this, another two hydrogens will be there. So 1, 2, 3 hydrogens will be getting produced here. And for production of this three, another three will be required. Another three will be there. So 3, 1, 2, 3 from this, and another 1, 2, 3, 4 for this. So 6 minus 2. One proton will be here, and for this reaction, another proton will be there. So 6 minus 2, total 4 proton are interacting here. So these 4 protons will be producing a helium 4 elements. So this way, this in the PP cycle, proton-proton cycle, the energy will be generated, and that energy will be coming out with gamma particles, means light, gamma radiation, and this occurs in the low mass stars. For the massive stars, uh, uh, while I'm saying the massive stars, I'm indicating those stars whose mass is much much more greater than 1.5 solar masses. So the 1.5 is a number which we call as solar mass is called as Chandrasekhar limit. I'll be coming to the Chandrasekhar limit later. For massive stars, we have another cycle called CNO cycle. C stands for carbon, N for nitrogen, and O for oxygen. So carbon, nitrogen, oxygen cycle. Here, carbon, nitrogen, oxygen will be acting as a catalyst, which will be helping the hydrogens to convert to helium. Here you can see one carbon 12 element. Carbon 12 is clubbing with fusing with hydrogen, and it produces nitrogen and also the gamma ray. From this nitrogen will disintegrate to carbon by producing a neutrino as well as a positron. Then this carbon 13 will be disintegrating to nitrogen 14, and it also with the help of a proton. Then this nitrogen will be converting to oxygen 15, and that oxygen 15 will be converting to nitrogen. Then nitrogen and hydrogen again that will be fused to produce helium. So here one hydrogen, two hydrogen, three hydrogen, and four hydrogen. Four hydrogens are acting to produce a helium, but um, carbon 12 is also used here. Nitrogen is used, oxygen is used. So carbon, nitrogen, and oxygens are acting like a catalyst to produce this hydrogen to helium. This occurs in heavier stars, which are massive stars, whose mass is more than 1.5 solar mass. Here, the energy liberation rate is plotted. You can see the temperature of if we consider the sun. Inside the sun, how the temperature varies. At the surface, it is 5,800 Kelvin, and at the center, at the core, it is 15 million Kelvin, means 1.5 into 10 to the power 7 Kelvin. So that amount of energy at that amount of temperature is required to produce this proton-proton cycle as well as CNO cycle. You can see here, uh, here in the y-axis, this log E means energy liberation rate is presented with respect to the temperature of the core. So here you can see that the PP cycle, the energy liberation rate is it starts a very lower temperature, like less than 5 degree Kelvin. And we can see here the liberation energy liberation rate starts very early for PP cycle, but for very late for CNO cycle. CNO cycle is work for the heavier object, and PP cycle work for the small or intermediate mass stars. Here we can see that for for sun, it's the temperature is 1.5 into 10 to the power 7 Kelvin, or 15 million Kelvin. And the sun can also possess CNO cycle as well as CNO cycle as well as PP cycle. But in the our sun mainly using the PP cycle to produce its energy. Here we can see that there is a equilibrium of this energy liberation rate, which is at around 1.6 or 1.7 degree, 1.7 into 10 to the power 7 degree Kelvin. So here we can say that if the temperature of the core is much more higher than the small intermediate mass stars, then CNO cycle will be the prominent. And for low mass stars or intermediate mass stars, PP cycle will be the prominent energy production process. So this indicates that how much of mass will be required such that we can achieve more temperature you can hold more temperature in the core such that you can you can choose PP cycle or CNS cycle. Okay, towards now I'm going towards the death of the stars. So till now we have discussed how the stars are forming. Stars are forming from protostars, and then from the protostar they are forming a main sequence stars. Here, a star. Here it is the star like our sun, means low mass stars. Then this is a very huge, massive star whose color is blue, which is, for example, it is regal. Then how it will be converting to the red giant or red supergiant, that we'll be discussing. Okay. Okay. Uh, the Loma stars goes for after red giant, they goes for planetary nebula phase. Then the once the all the masses, all the gases will be expelled towards through from the star. Then only one remnant is there, that is white dwarf for Loma stars. Whereas for other case, if it will be going to a supernova explosion, and from the supernova explosion, depending on the mass of the star, it will be either forming a neutron star or a black hole. So we are now going towards this how it will be forming a giant or red giant. This is the death of a sun-like star. So it all start with a protostar, then it will be a sun-like star. The sun, our sun is at here. Now, when the sun will be converting its energy, its mass to energy. Definitely, mass will be reduced after some billion years. So, if we consider that sun will be the total lifespan of sun is around 10 billion years, then it's already past half of it, or we can say that it's at the stage of 4.5 billion years. So till now, sun has already have spent a lot of mass, and that has been converted to energy. And this way, one time will be coming when the mass will be getting converted to energy. Then if this process will be go on till more 5 billion years, then definitely a time will be coming when the mass will be not able to sustain the gravity, because for to sustain the gravity, mass is required. So mass will be reduced, definitely gravity will be reduced. If the gravitational energy will be reduced, then definitely its gas pressure will be increased. So that the hydrostatic balance will be not there. So at that moment, the gas will be taking on dominating on the gravity, and that because of that the gas pressure will be because of gas pressure the sun will be swelling out. The temperature which will be required, because you see here, you see hydrogens are getting converted to helium. So helium needs to be fused. Then if helium will be abundant, then helium needs to be fused to more heavier element like carbon and oxygen. So the temperature will be required at around 10 to the power 9 Kelvin. So at that temperature, the core, if if the helium will be not helium will be getting converted to carbon, then the a carbon rich center, means core will be there. So at that moment, at the same time, um, the sun will be swelling out, and its radius will be go on increasing and increasing. If the our sun will be swelling out, it can reach up to the radius of uh, the uh, the Mars. So that much amount it will be swelling out. Okay, then one time will be coming that the gravity will be unable to pull any of its mass, any of its gas. Then there will be an explosion, and that explosion will be very beautiful to observe, and that will be forming a nebula, planetary nebula. So when planetary nebula will be forming, then whole of its gases, whole of its elements will be, except the core, they will be expelled to the whole of the space, and that will be spread out in the space. So the remnant will be only a white dwarf whose density will be around 10 to the power 6 gram per centimeter cube, and that will be carbon or oxygen rich. So this way, the sun or sun-like stars will be going to be demise. So here, the density is 10 to the power 6 gram per centimeter cube, and at the moment, the density is very huge in this small area, and here one um, uh, pressure will be acting here, and that pressure will be created by the electron degeneracy pressure. So electron degeneracy pressure will be giving an outward force, and definitely gravity will also be there because the area is small, and gravity and the degeneracy pressure will be counterbalancing with each other, and that at that phase this will be a stable white dwarf star, and that will be running for millions of or billions of billions years, and that will be that will be present as like this white dwarf for much more period. For example, we have a nearby star, Sirius B. Sirius B is a white dwarf star. So coming next to the lower part, when the mass of the sun star was very huge here. If it is a large star, definitely the process of production of energy is the same. CNO cycle will be there. So CNO cycle will be producing the energy, and also here the energy, sorry, the mass will be getting converted to energy. Mass will be reduced, gravity will be reduced, and because of that, the outward pressure will be take on. It will be more will be mm, dominating on the gravity. Then it will be swelling out, and when it will be swelling out, it will be, since it is a massive star, so it will be much huge. Real is a kind of that kind of star which will be forming a very huge star, a red supergiant star. And when it will be explode, then that explosion will be called as supernova explosion, and which will be leading to the death of the star. So this is a Crab nebula, which is formed because of supernova explosion. And depending on its mass, if the mass of the star is more than 1.5 solar mass, then it will be forming a neutron star. And in the neutron star, what will happen? Because as we see that uh, the critical temperature for white dwarf is critical density for white dwarf is 10 to the power 9 10 to the power 9 gram per centimeter cube. If the um, density will be more higher, then what will happen? The electrons and the protons will be fused together to produce neutron. So in that case, if the density become more than 10 to the power 9 gram per centimeter cube, we can observe that that transformation of the electrons and protons to neutrons. So that will be producing a neutron star. So in the typical neutron star, the density is around 10 to the power 14 gram per centimeter cube, which is much more greater value than the critical density of fusing this electron and proton. So a neutron star will be formed that way. If the mass will be more, more than 3 solar mass, then it will be producing a black hole, and the density of black hole, typical black hole, is of the order 10 to the power 28 gram per centimeter cube. You cannot imagine how dense it is in a per centimeter cube. There is a 10 to the power 28 gram of element. So you cannot imagine how dense it is. So this way the stars get demised. Okay, so yeah, these are a few beautiful and iconic supernova. This is the Crab Nebula that have been seen already. It's located in around 6,500 light years away from here. And the notable feature is that it contains rapidly spinning neutron stars, or the pulsars. So neutron stars are present here. From this nebula, Crab Nebula, lots of stars are getting formed. So they are neutron stars, and they are bright and filamented structures are there, which is visible not only in the visible lens, but also in the multiple wavelengths that has been observed. So it is very beautiful to see. Cassiopeia A is another supernova, and it's around 11,000 light years away from our place, and it is the brightest radio source beyond our solar system, and it is famous for the colored X-ray and optical image showing as expanding cell of gas. So it is made up of gas, and it is very beautiful, spectacular to observe. And this is the Tycho supernova. Tycho, this name is from this astronomer Tycho Brahe. By his name, this supernova is named, and it is in the Cassiopeia constellation, which is around 8,000 light years away from here. And this is we observe this, and it revolutionized the understanding of the universe. And this remnant is observed in X-ray as well as in the visible ray. So it is very beautiful to see. All of these are from are stardust, and those stars and molecular gas are forming the new stars in this nebula. Okay. Coming towards end, this is a cosmic cycle. We can see that if a sun-like star is there, from the from the nebula, star-forming nebula, it forms a protostar, then sun-like stars, then red giant, then planetary nebula, then white dwarf. And when it will be exploding, that explosion will be produced the gases again. So from these gases, a new star can be born. For massive star, again, the same process, protostars, then massive stars, then red supergiant, then supernova explosion, and black hole or neutron star. And the remnant, then the explosion, the gas and dust which is going out, that will be forming again star forming nebula. So this will be recycled. This is both for both cases, low mass stars as well as massive stars. The process is recycling. So we can say that the supernova scatter heavy elements across the space. These materials form new stars, planet, and eventually the life. So in a very real sense, we are made up of sun's stardust. So we can have the evolution of the stars at a glance. but by the use of the HR diagram or Russell Hertzsprung diagram, which is developed by Hertzsprung and Russell in 20th century by observing the luminosity and plotting it against the temperature or the spectral class. So what they have done, they have considered a star cluster. They have selected a star cluster. Here they actually considered the Hades cluster, and this cluster, this Hades cluster, all the stars which are available are almost at the same distance from the sun. So these stars, and those stars are producing different colors. So observing their colors or the luminosity, they have observed that their um, luminosity as well as their temperature are different. So what they have calculated their luminosity and plot against temperature. Then they have observed that they form a peculiar structure like that. So all these luminous objects are bluish luminous objects are fall in this region. ম্যাডাম এখন মিটিঙত আছো, অকণ পাছত ফোন কৰিম দেই। Then yellow stars fall in this region, and the red small objects are fall in these regions, which are less luminous, and temperature is reduced like this. And few of the objects are fall in this region. So by observing this, they can observe, they say that this sequence is called the main sequence. All the stars will be following this path. Once their path here will be completed, they will be going towards this, where their size will be enhancing, as well as their color will be enhancing, their luminosity across their temperature will be like this. They will be very luminous, then temperature will be less. Okay, and few of the parts are also here, but in the Hades cluster, they are unable to find any part here. So they have termed this sequence as the main sequence. This sequence is the giant or red giant, and this part are called as white dwarf region. So main sequence, red giant, and white dwarf. There are three regions in HR diagram. So that has been plotted. So we can see that if we can see the mass of the masses on the main sequence, the mass on the main sequence stars are fall like this. This is 20 solar mass, 5 solar mass, 2.3 solar mass. Then our sun is considered as 1 solar mass. Sun is considered as one unit. Okay, then if they the stars are towards their end of their journey, so then they will be forming the red giant. So the red giants and super giants will be here in this region, and the Betelgeuse and other stars. Betelgeuse is going to be explode or explode. I don't know, but it will be forming a red supergiant. Then, if sun-like star will be demising, then it will be forming a white dwarf, which will be falling in this region. And as I said, Sirius B is a white dwarf, and that white dwarf will be falling in this region. So this HR diagram gives a complete revolution, that gives a complete revolutionary track of any star. Say, for example, you have identified a star, and you have to calculate the luminosity of it, the temperature of it. Then if you plot, put it in the where it will be falling. Say, for example, it falls at this point, then you can immediately know that, oh, it is a red giant, or it is a red supergiant. If it falls here, then you immediately can say that it is a white dwarf star. So you can know the present status of that newly identified star by using this HR diagram. For size also, uh, this line is considered as the reference line because radius is one solar radius. Above this, the radius will be go on increasing. Here you can see this. This line is for 1000 solar radius, and lesser than one solar radius. These are for dwarf planets, or sorry, dwarf stars. So this way also you can determine the size of a newly identified star. So these are the how we can have an idea of how the star will be forming and how it will be getting demised and what will be the final stage of a star. So all of this can be understood from this HR diagram. Okay, with this, I would like to finish my talk, but before going to that part, I would like to show you some pictures that we have captured. This is the annular solar eclipse, 3 phases, and this is stacking of the different frames of Jupiter. This is blue moon, blood moon, and eclipse moon captured in 2018. This is the moon, first quarter moon, Jupiter and Saturn. Yeah, this is Messier 27. This is a very beautiful um, uh, nebula, and it is called the Dumble Nebula. We have captured it in Tezpur University in Assam. Yeah, this is also captured in Tezpur University, Assam, and we have processed it, but processing was very raw. And this is Orion Nebula. You have seen the upside down Orion Nebula picture in the first or second slide. But since we have captured it through our telescope, so a telescope always gives an inverted image. So it is become upside down, and you can see this area was captured, and where a very huge dusty gas plasma are present in the Orion Nebula, and which is very potential area for production of different stars. And this Orion Nebula is around 1300 light years away from the sun. These are few activities of our group. We have gone to different places for popularizing the astronomy, and one of them that has been conducted in village and remote schools. And here you can see these pictures. This is the picture of the solar eclipse, which is there in 2020. And at that time, I was there in a village, and I was working with these kids, and the kids were very much fascinating, means very much excited to witness this solar eclipse, but their um, parents were not allowing. So I called all the parents, basically the mothers, and they have observed it through our telescope, and they can realize, oh, there is no such kind of things that we cannot see the eclipse. We should not go outside during eclipse. Those type of misconception were removed at that moment. We also keep on conducting different awareness camps in different schools, and these are few pictures of it. So I would like to give a small message that let's your curiosity be your compass and the stars your destination. For the universe awaits the brave hearts who dare to dream beyond the earth. So with that, I thank you everyone, thank you all, and I'm available in this WhatsApp number. With that, I thank all the organizers, and I now give the platform to the host today.
Yes, thank you so much, sir. Thank you so much for this truly fascinating session on the evolution of stars. From the births of stars in nebulae to their magnificent death as supernova, your talk took us on a journey across time scales. And yet you made it feel so alive and understandable. You didn't just explain the stellar evolution, but you made us feel it. So, on behalf of everyone here, I want to express our sincere gratitude for your time and your knowledge. It was a pleasure having you here.
Thank you so much, Anjali.
May I come
Now
in,
I'd like to
Dr.
open.
Nitu?
Yes, yes, sir.
Okay, hello, how are you?
I'm good, sir. How are you, sir?
I'm very good. Nice to see you in this program.
Yeah.
Unfortunately, I missed part of it because there was another meeting. We are
Okay.
going to have a workshop on question item designing. So I was in that. But at least I could steal some time from there to join so that I may at least talk to you.
I'm
And I
very
think,
honored to hear you, sir.
your pictures really were very fascinating. And let me tell the audience here that I was with Dr. Nitu in his university. Now I think he has shifted from there,
Yeah.
but earlier he was there in that university where he had created a wonderful setup to watch the sky. And rather, in there we had a student symposium of the IAPT, and he also took a sky watching session for the participants there on the roofs of that particular university itself. And I think he is one of the best examples of where there is will, there is a way. So he
Thank you,
created
sir.
that way there. And I was really fascinated by last set of pictures which you showed. I can still see them on the screen here on top in the PPT itself, where you talk to the mothers that please let them see the solar eclipse. There is nothing which will happen to them. And then you are using a globe also, to demonstrate something here. This is just wonderful. And how I think you were trying to show the shadows of the eclipse on the wall or of the sun's
Yeah.
picture on the wall, pinhole effect kind of a thing. I think this is just great. So we are very happy that Nitu is part of this NASNI group. Nitu, I hope you know this NASNI group now
Yes,
in
yes.
more detail. Professor Hemant is the anchor for this program. And NASNI is a very interesting Hindi word. It stands for small but constructive. This is the name which people give to the girls. So we have given this group this name, small but constructive.
Constructive, right?
So that is what we are aiming at. And I am very happy to see Anjali, taking over. If young people start participating, I think that is the best thing which can happen to any group. After all, why we are doing it? We are doing it for curious young minds, and nothing like getting inspired from young students who join us and do things. I can see Soham also sitting here. There are so many people around, and it's just great. Swati is also there, I believe, and she is. Professor Bharat is also here. Ma'am Vandana is a permanent person who comes and talks about it. Dr. Yogesh Bhatnagar is here. He is a very seasoned, person as far as astronomy is concerned, and his expertise is in the stamps of on astronomy and physics. IAPT ran for 3 years his column in the bulletin. And I have been telling and requesting Professor Yogesh that please bring out a book out of it. We want to really make it an IAPT publication, maybe to begin with an e-publication, but we can think of publishing it also. It's a wonderful set of books. Even today I saw he had posted a very interesting information. And we have people like Professor Bharat who are in that area where sky watching is a pleasure in the country. So I think what more I can say. But Dr. Neetu, I assure you that I will watch your lecture.
Thank you so much, sir.
So thank you. Thank you very much. Himanji?
Thank you very much, sir, for your encouragement. Miss Anjali, please see the chat box. We have any question?
Yes, sir. If you have any questions, you're welcome to unmute and ask directly or type them in the chat so that I can read them for you. Everyone is welcome to ask questions.
Dr. Neetu, I want to ask one question that you have long experience of sky gazing and helping people to understand about the sky. Do we see any quantitative or qualitative change on the students or parents, and while they are going in higher education, does this affect the student to choose the subjects in higher classes?
Yeah, we have observed very recently that students in very infant stage they are very much fascinating to subjects like astronomy, astrophysics, and all. But when they go into deeper, then we have seen that they are more towards the professional courses. So professional courses like engineering or technology or towards a medical field. So very less amount of students which have very keen interest in physics and astronomy or in the subjects like this, royal science, they stay back in this domain. So anyway, we have this way also we have only those students which have high interest in this subject. So it one way it is better, but the number is definitely reduced.
Thank you.
Sir, I have a question.
Yeah,
Sir,
please.
so that story was really, as Dualia sir also mentioned, it was really fascinating to know how you convinced and taught those village people or those students and their parents that you can watch the solar eclipse. So I wanted to ask, what were especially the mothers, like what were their concerns regarding the solar eclipse? Why were they not allowing them to watch? And then how exactly did you convince them?
Here in our place, I don't know whether it is there in in different parts of India or not, but we have a misconception that during the solar eclipse or any kind of eclipse, it may be a lunar eclipse. People are not allowing our elderly people are not allowing the kids to go out. They say that some um, some bad effect will be happening. Uh, but that is not true, and never be true, because we are doing astronomy. We are knowing that if any solar eclipse is occurring, means the sun as the moon is coming in front of the sun, and then the shadow of the moon is casted on the earth, because sun, moon, and the earth are aligned. And the same is happen in the shadow of a tree also. So all this will be aligning. So shadow will be casting. So there is no there should not be any misconception. But some what is called, we can this I forgot this terminology, but this misconception has to be removed. So what I thought that if I ask the ladies of the home, means the mothers of the home, then it will be beneficiary benefiting the session. So I request all of them, few of all the houses, and a few of them are turned out, and they came in, observed it, and the moment they observe it, then they start calling their kids. So all of the kids are coming out, and the kids were also observed it. One thing I realized that if we can educate the mothers, educate the grandmothers, then half of your job is done, because mothers or grandmothers are the first teachers. So if you do that, then you can 50% success is there. So I able to make it happen, and later on they are asking when the next event is there. They are very much interested to observe the next event. So I told them that it come time to time. I'll be informing, and you can witness. So this way the science can be explored, and to the general public also, and can be educated. So this way I'm trying my best to educate to the general public.
Thank you so much, sir. This was super inspiring.
Thank you so much. Thank you so much, Anjali. I also thank to Aluwalia sir, because he is an inspiration. Thank you, Hemant Kumar sir, because of you, I'm able to give this presentation today.
So I think there is no more questions. Anjali, we can wind up now.
As I already thanked Dr. Neetu sir, I would like to give a special mention to Dr. P.K. Ahluwalia sir, Dr. Arvind Kulkarni sir, Dr. Vandana Luthra, Dr. Redhma Desai, Dr. Yogesh Bhatnagar, Professor Bharat Kangude, Professor Govinda Lakhotia, and Hemant Kumar sir and Ranjita Das ma'am for being here. Your presence made this session more special than anything. Dr. Nitu Borgohain, thank you so much once again for this brilliant and absolutely phenomenal talk. We look forward to hear from you very soon again and get this inspiration and fuel to learn science and propagate and explore science the way it should be. Thank you so much everyone for joining us today. I extend thanks from my Singularity Club as well, and I hope this was just the beginning of this collaboration. And we look forward to participate with NASNI in such events and sessions even more. Thank you so much.
Thank you so much, Anjali.
Thank you very much, Anjali, and all the participants. Thank you very much.
Thank you and
Thank you.
bye. And
Thank you.
Ma'am Ranjita, your selection was wonderful. देखो आप नीतू साहब ने क्या काम करा है ना, wonderful.
Yes, sir. I'm so happy to see him also. Yeah. Yes.
Okay.
Thank you, ma'am.
Yeah, I was very happy to see him.
Thank you, ma'am. Thank you.
I hope in Royal Global University also you have all the things, the facilities.
Yes, we have a observatory there. I'm trying to explore in this next session, because nowadays the weather is very unpredictable.
Yeah.
So probably from the October or November we'll be start gazing.
Okay.
And I'll be inviting you also sometime. You can come.
Sure.
Okay.
Okay.
Okay. Thank you, ma'am.
Thank you all.
Anjali.
Thank you very much.
Thank you, sir. Thank
And
you.
good night.
Good night. Good night, sir.
Thank you, Anjali.
Thank you, Anjali.
Thank you.